In classwork 7.3, we are going to learn how to graph the other 4 trig functions, and we're going to do this over 2 days. So we know the graphs of sine and cosine, and we've been using them a lot so far. I want you to see how you don't need to fully memorize 4 new graphs, but understand how you can create them from graphs you already know. So what I'm going to ask you to do is to create the graph of secant. First, you're going to use dashed curves and sketch the graph of its reciprocal function. Who is secant's reciprocal function? Is it sine or cosine? Cosine. So if you see that you need to graph secant, what you want to do is first graph cosine. And notice that this time I have the grid set up with by pi over 4s. Cosine starts at its peak, its top, at 0. At pi over 2, it's back to the midline. At pi, it's at its lowest point. Then at 3 pi over 2, back to the midline. And at 2 pi, it's back to its highest value again. So I'm going to do a dash graph of it. That's one cycle of my cosine graph. I'm going to continue it out and draw it all the way to the edge, both directions. So I'm going to go backward a little bit and go forward. Okay. Now, I have a lot of questions here, and it's meant to get you to see the numbers of how cosine, all of its values are reciprocating. So when cosine is at its peak, its y value is 1. But what's the reciprocal of 1? Yeah, and this is why I specifically pointed it out, because it's just, when things seem too simple, they end up being hard because you're expecting harder. Reciprocal means 1 over, and 1 over 1 is then going to be just the number 1. So I want to emphasize to you that that means that the graph of secant and cosine share the same exact points when you are having that y value of 1. Now let's go back to the graph. Do you see where all the y values 1 are? The graph of secant shares those top peak points. Now, what is the reciprocal of negative 1? And you say, almost too simple, negative 1. Now look at that, that's the same number. That means that where I have the low points of cosine, the secant graph shares those points also. So if you are able to graph a cosine function, all of its highest and lowest points are also points on the secant graph. That is really, really, really convenient. But now I want to talk about some of the other numbers, because we want to notice that those are the highest and lowest y values for cosine. All the other y values of the graph as I'm going along, all those other y values are in between -1 and +1. So in part C, I want to talk about there are places where cosine crosses the x-axis. And when it crosses the x-axis, its y value is 0. So this is actually a tricky question. What is the reciprocal of 0? Like this one's really, really, really tricky, and you haven't really gone deep into it yet. This is undefined. But let's talk about what kind of undefined that's actually meaning. So what I'm going to do is I'm going to talk about what happens when that denominator is getting close to 0. If I go back over to Desmos and I look at 1 divided by x, but I am looking at my x near 0. What's happening to this graph when x is near 0? In fact, do you remember that we looked at the graph of 1 over x back when we did rational functions? And do you remember that when that denominator was 0, that's where we had the vertical asymptotes? So what I want you to be aware of is secant x has vertical asymptotes when its reciprocal is 0. So the question, what feature does the graph of y equals secant x have when its reciprocal is 0? And that would be it has vertical asymptotes. So now use this information to graph that feature, vertical asymptotes, everywhere that your cosine function is 0. So I'm going back to the graph. And I've got the cosine is 0 here, 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 here. Let's draw vertical asymptotes. So just some dashed lines. Oops, that was wrong. Yeah, only at 0. Okay. Now, part D. If you reciprocate numbers between 0 and 1. So if I reciprocate, for example, 1/2, what is its reciprocal? Another number between 0 and 1 would be 2/3. What is that reciprocal? So we can keep thinking of more numbers between 0 and 1 and looking at the reciprocal. Now I'm keeping these fractional so you can see a little bit better. What if I have 1/8? What is the reciprocal of 1/8? 8. What are you noticing about the size of numbers when you reciprocate numbers between 0 and 1? what are you going to get if you reciprocate numbers between 0 and 1? We're going to get numbers that are larger than 1. And in fact, some aren't going to be all that big, but some of them are going to be large. And if we looked at 1 over 100 for an x-coordinate, that's going to give a reciprocal value of 100. If I look at a number that's just barely less than 1, 99 100ths, its reciprocal is just barely bigger than 1. So I have anything from just barely bigger than 1 all the way to huge toward infinity. Now, what if I just look at the reciprocals between -1 and 0? So basically same numbers, but negative. What are the reciprocals of these negative numbers? Now, if I needed to explain the interval of numbers, larger than 1 to infinity means numbers that are 1 to infinity. Numbers that are smaller than -1, but big negative numbers are negative infinity to -1. So what I'm trying to do is help you to see the following. In this section, I'm dealing with numbers whose reciprocals are bigger than 1. And what are those vertical asymptotes there for? When we did rational functions, those vertical asymptotes had to be followed. So I have a shared point and then positive numbers from 1 all the way to infinity. I'm going to see exactly the same thing every time I have my peak points between asymptotes. Then if I look at sections where the y values of cosine are between 0 and -1, those are just basically the same thing, but flipped over the x-axis. They share this one point that is lowest on cosine and then follow their asymptotes, but stay negative. So that is how you can draw a cosine graph. And from that cosine graph, you can draw your graph of secant. And let me say again that what you're going to do is first draw your cosine graph. Everywhere it hits the x-axis, do vertical asymptotes. Everywhere that it has a peak, you've got these little shapes. They almost, I know people like to say they look like parabolas, but they're between asymptotes, so they're not parabolas, but I know people like to say they look like them. And then everywhere that you have your low point, that's a section where you're going to draw one of them heading downward. As you look back at this, do you see that graph cosine and all of a sudden everything else just shows up? If you realize what it is that you're doing. Okay. Now, cosecant is going to go faster. For cosecant, who is cosecant's reciprocal function? And did you catch the vertical asymptotes are where cosine crosses the x-axis, where cosine is 0? Okay, cosecant, reciprocal is, and everybody all at once said sine. So let's do exactly what we just did, but based off of the sine graph. First, I'm going to plot important points on sine. Sine goes through the origin. It hits its high point of 1 at pi over 2, goes back to its midline at pi, down to its lowest point of -1 at 3 pi over 2, and then back to its midline at 2 pi. And then I'm going to keep that process going forward and backward. And I'm going to dash draw. And once you get better at this, you may not even need to dash draw. The vertical asymptotes of my cosecant graph occur where sine crosses the x-axis, which is all of these points. So now I'm going to draw all these vertical asymptotes. And then if I look at where this graph has its peaks of a value of 1, that's where its reciprocal trig function, cosecant, shares a point. And then it has to follow those vertical asymptotes. All the low points of -1, that is where sine and cosecant share points, and then it has to follow the asymptotes. And when I look at secant and cosine pairs, and then cosecant and sine pairs, I see it as little kindergarten crushes of, like, one runs toward the other one, gives them a quick kiss, and runs away. Never to be seen again. I don't know. But kiss and run away. That's what these pairs of graphs do. Now, some tough things to fill in here. Range. Range is looking at y values. The range for both secant and cosecant, what I want you to see is what isn't in the range. What is not in the range of secant and cosecant are the y values in between -1 and 1. So when I state the range of these two functions, they go from -infinity until -1, but they include that y value of -1, so it's a square bracket, united with, starting up again at 1, inclusive of 1, square bracket, to infinity, and infinity gets the round brackets. The domain of the two functions are everything except their vertical asymptotes. Now, secant had vertical asymptotes where cosine was equal to 0. So that is pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2. Do you think you could write that as a pattern? There are different ways to write this. You're probably going to prefer to not use the interval notation. It's horrible to use. It's basically all real numbers except. Except for pi over 2 multiplied by any integer n. I find that to be an easier way to write it. When it comes to cosecant is sine's reciprocal. Sine is equal to 0 at 0, pi, 2 pi, 3 pi, negative pi, 4 pi. So with that one, you could say that it's all real numbers. But x cannot equal pi multiplied by any number. Although I realize right now that I just wrote this in a way for this first one, n can't be 0, then that doesn't make any sense. So now I'm giving too many exceptions to the rule. So what I'm going to do is write it this way. Unfortunately, I have to write it this way unless I say for any n except 0. It gets annoying. And the way I wrote it in the classwork, how did I write it in here? Okay, yeah. And I don't need to say this pi part. I can say just the pi n. And I also use the word except. So by writing, I just realized I'm confusing you because it's an issue of double negative. And I don't want us to get overly concerned with the words. When it says except, that does mean the same thing as but. And the way I wrote it, I actually am double negativing it, which in English means is incorrectly written. So if you don't include the word but, then that makes sense in English words. This is where grammar meets math in a very unfortunate consequence. Okay, now, how long does it take for an entire cycle? To go through an entire cycle of one of these, I have to go through an upward facing U and a downward facing U, and then the cycle begins again. So you want to notice that the period of these two graphs is 2 pi, just like it is for sine and cosine. Now we have 2 minutes left. With those 2 minutes, let's get started prepping for graphing tangent and cotangent. And If you pull out a unit circle, you can take a look at it to help you see what these should be. So I'm going to I'm just going to draw a quick unit circle. The angles that we look at on the unit circle are 0, pi over 6, pi over 4, pi over 3, pi over 2. So I'm going to start with those. For 0, I have my y-coordinate divided by my x-coordinate, or you could say slope, and I'm getting 0 for my tangent. Every time I know a tangent value, cotangent is its reciprocal, and the reciprocal of 0 is undefined. And there's the bell. So we'll pick up here tomorrow, and your only homework today is the homework corrections from 7.2. That's it.